Hi guys. So now I'm going to, in this video, start the process for derivation of what is called Gauss's law. Right? Now, we have talked about Coulomb's law. And what does it tell us? It tells us that there are two charges. So let's say there is one charge here plus Q1, right? And there's another charge here, right? Plus Q2. Right? Then we know that, and if the distances are, we know that the force of, in this case, force of repulsion between them, right? F would be given as K Q1 Q2 upon R square, right? And correspondingly, if at this point or at any point, if you look at the electric field due to, let's say, only this charge, right? The electric field, right, because of charge Q1 would be nothing but K Q1 upon R square, where R is the distance between the point and the charge. Okay? Now there is another way to state the same thing, right? But it looks very, very different, right? And that is what we call Gauss's law, right? Gauss's law also will tell us, for a given charge or for a given charge distribution, we can find out what is the electric field at a given point of time, right? So here this is using Coulomb's law. Now I'm going to talk about Gauss's law. So I will first state what the Gauss's law is, and then we will take the different elements and start breaking it down and trying to understand. So let me just give you the blunt statement, the statement of Gauss's law. It may not make a lot of sense to you, but once we have gone through the explanation, it will start making sense, right? So what is Gauss's law? Gauss's law states that integral over a closed surface E dot ds, right, equals Q inside upon epsilon naught. Right? This is Gauss's law. Right now, it will not make a lot of sense to you, and that's fine. So let's now start kind of looking at individual elements of this formula, right? And then I will actually derive it using Coulomb's law, right? Using E equals K Q1 upon R square, this concept. So now let's look at each of them. So what is this telling us? This is telling us that if there's an area element ds, and if I take a dot product of E electric field at that point and ds, right, over a closed surface, right? What is a closed surface? Closed surface, let's say a sphere or can be any envelope, any kind of shape, which covers some space, right? It's a three-dimensional closed space, right? So that is equal to the charge inside that closed space upon epsilon naught. Right? So now let's start with E dot ds. So what does that mean? E dot ds, right? So this term I would like to understand. So now this may kind of bring an interesting question in your head, which is that, we have E dot ds, so which means we are saying that this is a dot product of two vectors, E and ds. What is ds? ds is the area, right? Now, is area a vector quantity? So think about it. So let's say there is some flat, we have taken just a flat surface, right? It's, let's say, spherical or oval shape or whatever. So this is the surface, right? I'm looking at I'm looking at from the side, right? So now is surface area or is area a scalar or a vector quantity, right? So now let's say if I hold my hand like this, right? So think of this palm as this flat area, right? And this has got some direction, right? So now I'm holding it like this, now I change like this. Now the area, so something has changed. What has changed? The direction, the orientation has changed, right? So we can represent area as a vector quantity, and the direction should tell me how is the area, how is it oriented, right? So now the question is, how do you determine, or how do you describe the direction of an area element, right? Now just think about this. Let's say this is my palm, right? This was, let's say, flat surface, right? Now what would tell you the way I have put my hand, the way I've held my hand, in what direction? What would describe it for you, and tell you exactly, how I'm holding my hand. So now I'll just give you the kind of, the way to think about it. If I take a line which is perpendicular to this area, right? If I tell you where this perpendicular is pointing, then I know where the area is. So let's say this is the direction of the perpendicular, which means the area is like this. If I say this is the perpendicular direction, then area is like this, right? So essentially perpendicular to an area, right? A line perpendicular to the area will tell me, can help us understand what is the orientation. And therefore for any two-dimensional flat plane area, right? The perpendicular, right? The perpendicular to it is we call that as the direction of the area, and therefore now I can call it, now I can consider area as a vector, right? So now ds, right? Now this is, its magnitude is equal to the area of this element, and its direction is the direction of the arrow, right? Now obviously there is a question here, which is, there are two perpendiculars. So if I have a surface here, I can have one perpendicular here, other perpendicular in the opposite direction, right? So which is the right direction? So now there is no hard and fast rule. So it depends upon what context. Here in this equation, right, we will talk about it. And here if let's say this is a closed surface, think of a football, let's say, right? So this is the inside. So at any point, the area vector will take as pointing outside. Right? That is in this case, but in general, area can, both the directions are possible. So depending on the context, we'll have to decide. Right? So far so good. So we have described, what area, what ds vector means. Right? Now what is E dot ds? Right? So this we are going to give it a name. We'll call it electric flux. Electric flux. Right? And what is this? So we will now define that, if I have, let us say, an electric field, if I have some electric field, right, and let us say there is some area, right, there is some area which has got, let us say, and the surface area is, let us say, delta S, or I've taken ds, and you can think of ds as like an infinitesimally small thing. This is small, but this is not infinitesimally small. It doesn't matter, right? So now I'll define my flux, right, delta phi, right, small amount of flux, delta phi as E delta S cos theta, where theta is what is theta? Theta is the angle between area vector, right, between delta S vector and electric field. This is the definition, right? But now, what does it really mean? So let me just try to now give you some intuition. So visualize that, we have talked in the lecture, in the video on electric field lines. We said that we can visualize electric field as bunch of electric field lines, right? And what did we say there? We concluded that we can think of the number of field lines, right? Number of lines, right? Lines per unit area, right? That is kind of proportional to your electric field, right? If you're not sure, like refer back to that video. But there we showed that we can think of we can say the number of lines per unit area is proportional to the electric field. So if let's say in some place, let us say the lines are very, very close by, which means the field here is strong. Whereas if lines are very far off, then the field here is weak, right? Okay, so now let's take the simplest case. So let us say this is my electric field, right? I'm taking uniform electric field just for simplicity. And now let's say I take some area here, right? And this area is perpendicular to the electric field, right? And this area, let us say, is delta S, right? And the electric field, constant field, its magnitude is E. E is constant everywhere, right? What will be E delta S? E delta S is telling us what? E into delta S. Number of lines per unit area is proportional to E. So we get a sense of the strength of electric field from number of lines per unit area. So which means electric field into area. Electric field into area is nothing but number of lines, right? See, if I make the area bigger, right, the number of lines crossing will go up, right? So we can say that this is a measure of this gives us an idea of the number of lines flowing through the surface. Right now I'm taking both as perpendicular, okay? In this case, E vector is perpendicular to delta S vector, right? So this is, let's say these are the lines and this is the area, it's perpendicular, okay? So for this case, my E delta S, right, is telling me the number of lines, right, crossing delta S, okay? And the logic is this, right? Okay, so now so far so good, right? Now this kind of also gives a sense of why we call it a flux. The word flux in English means flow, right? So here you visualize that when we say electric field, right, we are visualizing that electric field lines are flowing through it, right? So bigger the area, the more are the number of lines flowing through the area, right? That is why we call it flux. Okay. Now next is what if this is not true? What if electric field lines are not perpendicular to the electric field is not perpendicular to the area? So let us just again we'll visualize. So let us say this is the direction of electric field, and I have my hand held like this, right? Now let us say if I start changing the direction of my hand, right? Now here now my hand is I've moved it by 90 degrees. Are there any lines passing through my area? No, right? It's now 0. If I have say at 45 degrees, then lines are passing, but the numbers have gone down, right? Now the number of lines passing through this would be the highest, less, finally it becomes 0, right? So which means the angle between the electric field and the area vector has something to do with this. Now let us understand this, right? So first case is let us say this is my electric field, and this is my surface that I am looking at, through which I am calculating the electric flux, right? Now think of this as I am viewing it from the side, okay? So it's like my hand here, I am viewing it from the side. So I am just able to see the length. I am not able to see the breadth. I am not able to see this part. I am able to just see the length, right? Now imagine that instead of keeping it like this, now I move it, and now it makes an angle. Now I moved by some angle theta, right? Now what is the angle between the? So earlier before I switched here, right here, this was the electric field and the area both had the same direction. Now the area has got this direction. Electric field still has the same direction, right? So now this theta is the angle between the electric field. This is my delta S vector, and this is my electric field vector, and theta is the angle between them, right? Now as you can visualize what's happening, now the number of lines crossing this would have gone down. Why is that? Let me just show you. So earlier, if I draw the same length, right? So let's say same length here, this would be the length. The number, let's say I'm drawing 1, 2, 3, 4, right? Let's say 4 lines here, right? And here again 1, 2, 3. I'm drawing just certain number of lines, right? So now let's say this is a certain number of lines that are crossing. Now when I have bent it like this, now what's happening? Now this line 1, 2, 3, 4, 5. Now certain number of lines are still crossing, right? But this line now is no longer crossing this. This line will now actually not cross this. A line here also would have not crossed this. So number of lines crossing my area vector, my area kind of goes down. If I let's say if I were to take an extreme case, not extreme case, but let's say either theta is larger, I were to, let's say, further move it like this, right, and make it something like this. Now this line is crossing, this line is crossing, this line is crossing, right? But now this line is not crossing, this is also not crossing. So now the number of lines crossing my area is going down. Same thing, more, less, and finally it becomes 0, right? Now how much will be the how many lines will be crossing? It depends upon what is the projection of area perpendicular to the not perpendicular. What is the component of area which is in the same direction as the electric field, right? So here this is the length, right? I can take this. If I look at this whole length, let us say is L, right? So half the length is L by 2, right? So this length, I'll just draw it here for cleanliness, right? So this is my L, right? And this is my L by 2, right? And now this is the direction of electric field, and this angle is theta, right? Now I need to take this length, right? And similarly, I'll take this length here, right? So this is L by 2, this is going to be L by 2 cos theta, right? And this also would be L by 2 cos theta, right? So now this total length from here to here, right? This length is going to be nothing but 2 into L by 2 cos theta, right? This is equal to L cos theta, right? Now the other side is still perpendicular. Remember, so if I let's say here in this case, what I did was I took this area and I bent like this, right? This length, the other length is still perpendicular. That is not changing, right? So if I look at the total area as if I'm looking at the shadow of this area on the screen, right? I'm looking at shadow, which is the area from here to here, this area, right? Then that would be, this area would be L cos theta into, let's say the other side was B, right? It would L cos theta into B, right? When it was here, it was L into B. Now it is L cos theta into B. So this is going to, and what is L into B? L into B is my original area. This is the delta S is the area of this whole surface. So L into B is equal to delta S. So this is going to be equal to LB cos theta, and which is equal to nothing but delta S cos theta. Right? So now if I ask you what's the number of lines passing through this, we will say that number of lines passing through the surface area when it's at an angle 30 at an angle theta is going to be delta. Now I'll say that my delta phi, right, which is my which is the flux I was talking about, right, is nothing but E into delta S cos theta. Right? And this is nothing but what I gave here, right? So this was the definition we gave, and now I have given you the idea behind that flux, like electric flux, is defined as E dot D dot delta S dot cos theta, and intuitively what it means is it is the number of field lines that are passing through an area element, right? So this is the definition of electric flux. In the next video, we'll continue moving forward. So our goal is to ultimately to be able to explain or to derive this law from Coulomb's law.